Okay, my outstanding friends, there's been a lot of confusion recently about what I did with the light experiments with Rod Warren long ago. Right after he got his cell phone, 2012, was this Galaxy phone, is what we use, S3. And I presented all this evidence to literally everybody and was, not taken well at all. So I had been writing papers and putting them on academia.edu so that at least it would be published somewhere. They won't let you publish, so if it's not published, you can't look it up. It's just not there. It's just your words running your mouth somewhere on the internet, like YouTube, like I'm doing now. But academia.edu, they let you publish up there, and then you can go up and look at these people's papers. And this was from 2015, Electron Flood Theory, from November of, but this went on for years of dismissal, well, at least a couple of years. And then I decided I had to do something. So I published there, and then I really started to ramp up my videos. But it never happened. They just ignore you. So when you make claims about particles and science and neutrons and quarks and hadrons and all these kind of things they come up with, when you make those claims and somebody else presents evidence that shows that you need to at least examine it, and you don't examine it and you refuse to examine it, then I say those claims are not valid, and the new claim, which is my claim, is valid and is now accepted by every top physicist in the world. It's accepted unless they will address my evidence, which I will show you right now. Okay, as you recall, this is electron flood theory. I finally presented it as a paper in 2015. And at that time, I called it vortex theory of dipole electrons. And they flood everything, and they condense to make matter. So all that's understood. Now, let's see what was happening at the same time in mainstream. All right, they're going into this 2p, 2h effects, which they don't understand. They're just starting to get into it, and it's all over the world. They're working together to try to understand these particles. Now, this is from MIT as well. They're involved in this same thing, and this is from August 2015. Now, I had sent this long before that to virtually everybody. I'm sure some of these know, but MIT for sure. Okay, I showed you the particles. You could see that it's 2p, 2h, and I sent all this to the professors at MIT long ago, and it appears they're not interested. As yet, MIT has not responded, and they never did respond. And this was from 2015. From December 2015, I finally wrote the paper because nobody would respond. Finally, I said, I'm just going to put these papers up. I got 45 papers up on academia.edu because they won't let you publish. So you get lost in the woods. Nobody ever sees it. And they still don't see it up here. And nobody will peer review virtually anything. Certainly none of my stuff will be peer reviewed. And I come with actual evidence. I mean, there's virtually no question. These are the same particles they were finding at CERN, the Fermi lab. It's just that I could see them with CMOS, and they didn't understand that. Because the particles I was using with light, they're made to be seen with CMOS. It won't destroy it. It will be destroyed if you threw a bomb at it like that. But if you threw a little particle like this, it's not going to hurt it. That's what it's made to absorb, is those particles. Stronger and stronger and stronger, brilliances, and it shows you all the different colors, and it's all fabulous is the CMOS. And they realize this, and they actually upgraded at CERN to use CMOS. But in the meantime, I was fighting like crazy, and I said, I'm not going to give this up. This is not right. How can you just ignore this and not comment on it? And they did, and they kept on, and it's been going on for 10 years. All right, I'm just going to cut really quick through the chase here. I had this up here in 2015, 2015, about dipole electron flood theory. I call it 2p, 2h, you call it anything you want. And I sent all this stuff to MIT professors long before I put this paper up, and to all the other professors, but MIT specifically. For some reason I got them noted on there, but I did. And I sent all my research to all kinds of people. Finally I had to I have 45 papers up here on academia.edu relating to all my different research topics. And they are kind enough to let you publish here and at least have an archive of what you've done, rather than not allow you to publish, is what happens with peer review. They say, no, we won't peer review you. Oh, I said, why not? I have evidence. And I said, it doesn't matter, we're not going to peer review you. I said, well, why? If I have the evidence, you're saying this, and I'm showing that that's not the truth, or I'm showing my position on it, I think you should at least respond, and they don't. You know, to have Fermilab showing these particles are the particles, the smallest particles they can find, and we're using light, which is much smaller than the particles they're using. They're using protons, mass. We're using light, which is just everywhere. And we accelerated that light. We've showed these particles. I can show light's being accelerated. That's not supposed to be allowed. From Einstein, he said, no, it's one speed. You certainly can't accelerate it. You can slow it down in other medium, yes. In a vacuum, it's supposed to just go one speed, never slow down. Well, if we can accelerate it, that shows you right there. And that's in this medium. So obviously Einstein wasn't right. And light has mass. And that mass is the black particles. Those black balls. They call them muons, muon neutrinos. And when they hit Cherenkov radiation, heavy water, they split. And the white goes into a shower like this right here. And the black doesn't go in, it bounces back basically. And they know all this. They have charts showing this exact same thing we have, only we can squirt it anywhere we want to. And the black comes back to it right about here. It starts really jumping back together. By the time you got out to about here, it would be back to being basically like light again. But in the meantime, you separated the white from the black. I don't care what you call it. I call it fission. If you break these two apart and these two apart, and you have nothing but black floating around here and there and white in a spray, that's fission. When it comes back together, they call that fusion. Fission, fusion. What do you see? Think about it for a second. What do you think? What do you see? If it started out like this, and that's what light is, and it is, because not only this, but the green ones are like that too. The blue ones are too. And you break the black from the white, that's fission. Fission means you break something apart, and there it is. And we show the same particles they're looking for at Fermilab and CERN. The muon neutrino is a black one. Electron neutrino is a white. And they might call that a sterile neutrino, the black being all by itself. It's supposed to be attached to the white. That's what the Dirac neutrinos are. This is pretty obvious. What I'm showing is correct. All right, so what is light? Well, light is when you bang some particle against another particle, they glow. These are glowing. These are gas molecules in the air. They have fields just like anything else. If you push against them, they push back, they glow. It's like when you shine a light into the darkness, you get a little glow, and this is as dark as it gets. And this is the light coming through, and this is the red laser. Now, you see how much glow is going on there? There's a little particle back in here. I'm not sure where it is, to be perfectly honest with you. It may be the particle is way back here. But its field has to go through all of these fields and push them out of the way. That's the red laser. And it's pulsed. Now, I think these are pulses, so I think it's probably right about here. And it's starting to accelerate. This is acceleration. This is not normal. There are other red fields around here that you don't see. But we'll be able to see them later. But this one here, you can see it's starting to accelerate. And then all of a sudden, it takes off like a rocket ship. See, there it is right there. It takes off and just shoots like a rocket ship. And that's just a particle. Now, remember I said there's other fields? Well, they're here. They're all over here. They're all over in here too. But you don't see them until they get illuminated. And why are they illuminated right here? That little lip looking thing. You see? That's the same as these. But this one was dead right straight through the Venturi, and it has to accelerate. These are being pushed back and against. You see this reverse field over here? You see those reverse lines? That's from this explosion. This is literally a subatomic nuclear explosion. And I mean that seriously. This is a subatomic, smaller than atoms, nuclear, same because it's the nucleus stuff, explosion. The particles exploded. And the energy release is staggering. There should be no reason whatsoever we can't harvest some energy there. It is, and there's no intervention here, nothing. You carry that around in a lunchbox. And all you have is a laser, you got a little Venturi, and then you got to have a little harvester there with a photodiode. And all that's all off-the-shelf stuff. This 10 years it's been laying around, and I've been talking about doing this for 10 years. I don't see why it can't be done. If somebody can show me a reason. They show all the graphs. The graphs show the energy level here going off the charts. This is how they start growing in energy. And the only reason these are showing up is because they're right in line with the Venturi. And they're spinning in a circle. This is down, upspin. And this is downspin. Wherever the glowy part is, down means the glowy part is down, and they only go up and down. They flip. And when they flip, they do what they call a muon wobble. Now these are other ones that are like photons, but they're never going to be seen. The only reason we're seeing them is because of all that backlash. And here they get crazy. Back here, you don't see them anymore because there's just not enough pushback. This is going that way. Now the green is basically, well, it's the same particle right there. Identical particle. There's no difference whatsoever. And you can see it's straight up and down, even though it's going off this way. Its spin is straight up and down. So all particles are made the same, all light particles, but it just depends on how fast they're spinning. If they're spinning this slow, and they spin in a circle. So if they're spinning this slow, you got red. If they do this, they're green. If you got here, they're blue. And then blue really goes. And the green is pretty fast, and the red is not so fast. And then I can show you that right here. This doesn't have the blue, but it certainly has the green and the red, and the green is much stronger than the red. And it's coming way out here, concussing again, just pushing the red out of the way. They're both coming through the Venturi at the same time, straight up and down Venturi. And they're showing some little flicks of red are up in here. But the dipole particles are the same as they are everywhere. So dipole flood theory is not a theory, it's the new model, basically, unless somebody can come up and challenge that model. I have not had a challenge, not one challenge yet, none, zero. So I'm waiting for that. Until then, I own quantum. See this? This just came out in August 2025 Scientists just admitted nobody really gets quantum physics. You can't get it using a standard model. All they have to do is walk away from a standard model and look at dipole electron flood theory, which is right here, and then they will get it, because it's very simple. It's just that you have dipoles, not one big, huge, solid, positive mass and a couple little tiny electrons. No, absolutely not. It's one for one, basically. And it may even be not that exact ratio. I'm not sure. Because the white ones, or the glowy ones, have no mass. So it's hard to say. At a certain point, do they take on a whole batch more? Because I think that may be the case. Your nucleus is made up of protons, and then they say neutrons. Well, there's so many protons, maybe the neutron, because the neutron number changes, it gets much bigger as you go down. They call them isotopes. There's a lot to think about here, but this is the new model, and it works. That's your dark matter, and it's gravity. Okay, like I say, I flooded the internet, and I flooded everybody. I don't know if I talked to this guy or not, or sent anything to him, but this is University of Wisconsin-Madison. And he's saying physicist turns smartphones into pocket cosmic ray detectors. These are the same particles we're talking about. And he said, soon the growing capability of your smartphone could be harnessed to detect cosmic rays the same way as high-end multi-million-dollar observatories. Yes. By adding a simple app. Now, these are, and that was then, when we were using it to see these particles. All right, this is how light spins. It spins just like that, just like a drill bit. When it comes through, you get most through the center, but then you create these very elegant repulsion patterns. Those aren't interference, like a floppy waves and this and that. Those are, you stay away from me, I'll stay away, you stay away. So you create these lines. Those are what they call interference patterns. They're not. They're repulsion patterns. This guy doesn't want that guy next to him, that guy doesn't want him. And so they set up border lines. All right, I showed you the green and the red. They're exactly the same. So is the blue. The blue is just it's just too fast to see. It comes in, you can't hardly see it. It's two particles. By the time it slows down enough, you can see that there's two particles in there, but it's just too fast. So we only could work with the red and the green. Now, I showed you acceleration, I showed you not acceleration. I showed you the same Fermi-Lab particles as ours. The same, the 2013 was the article, and I approached Don Lincoln at Fermi-Lab about that, and he said, "No, you can't see that with that," and it was kind of contentious. And eventually, I did go through Coursera to University of Geneva, and I told them about this, and by the time we were done, they agreed. Now he says, "No, you didn't. You never went there." Yes, I did. I went through Coursera. Now, I don't know how they do that. They may just have us students talking to students or something. I don't know. But Coursera, I went back and forth with them until they finally said, yes, CMOS does work, but for particles you're using, because we're using little ones. They were breaking their CMOS with the huge things hitting it. That's all. They were throwing piles of stuff like this at it. We were throwing these little bitty ones. And that's what they're made to accept. They're not made to accept chunks. That's why they upgraded to CMOS. Okay, these are Higgs fields. They're created both when particles come apart and when particles come back together. And these are the ones that are coming back together from the white spewing through, finding black particles just laying around apparently, because they turn into Higgs fields as soon as they splash into this. And here's one that you can almost see the little particle, and then it starts to take on a spin. And that's all I can say. These things are very, very powerful. They're very, very energetic, those little white splits. So I'm leaving it at that. again, this goes back to 2013, and I was fighting, and I'm still fighting today because they just won't. Nobody will look at this. I don't think that's the way science is made to work. I think you're supposed to engage. When somebody reaches out and says, "Please, can we talk about this?" At least there should be some discussion. You don't have to. They should say something. The only one that really responded was Don Lincoln, and I thought we might be able to get somewhere. But his immediate thing was, "No, that's nothing. That's I forget what he says. He didn't want to work with me whatsoever." And then he started to call me an embarrassment to science and a tinfoil hat guy and everything else. That was a little discouraging, since I had the exact same particles he had. And for him not to be able to understand that is beyond my comprehension. I can't believe somebody would see that and realize I'm working with the particles, the smallest particles they can find are here. I'm starting with light, which is basically the smallest particles there are, and we're splitting them and seeing them. And we're seeing them attached together. They call these gluons. There's so much here that cannot be dismissed. I wonder what his... I just can't imagine it, that's all. That's my opinion. But certainly this should be looked at. That's my opinion. Thank you.